Okay, in this video, we're going to be looking at inverse properties and how they relate to exponential expressions and logarithmic expressions. So, if I were to find the inverse for that exponential function, well, the way to find an inverse is usually start by switching x and y. So let's say I do that. I have x equals b to the y power. Well, then if I wanted to solve for y, which is normally the next step I would take as I find an inverse, I need to get y an exponent all by itself. Well, as we figured out, to solve for an exponent, you could use a logarithm. I could rewrite this expression from exponential form to logarithmic form. Meaning, if I were to rewrite this as a logarithm, I have the log base b of x is equal to y, the exponent. So, I've switched x and y, I've solved for y. It's a pretty cool deal. So what I'm saying is that y equals b to the x power, and y equals the log base b of x. I'm saying that those are inverse expressions, even inverse operations. An exponential function, a logarithmic function are the inverse of each other. Kind of like multiplication and division would be the inverse of each other. Keeping that in mind, if I'm saying that, I'll say that f of x is equal to b to the x power, an exponential expression. And g of x is equal to the log base b of x, a logarithmic expression. By the definition of inverse functions, I should be able to do this. So, just remember back when we learned about inverse functions, told you that this would be important to find. If I were to look at the f of g of x, if I compose two functions that are the inverse of each other, my result is supposed to be x, the identity function. So, if I find the f of g of x using these two functions, the f function is b to the power. So I take b raised to some power. Well, that some power is the other function, the log base b of x. So b raised to the log base b of x, this is the f of g of x, has to equal x because these are inverse functions. And when I compose inverse functions, I get x as a result. Okay? Now, if I were to go the other way, find the g of f of x, I'm supposed to get the same thing. I'm supposed to get the identity function x. Well, here we go. Function g is the log base b of something. That something is the other function, b raised to the x power. And what's that supposed to equal if these are inverses, which they are? Well, it's supposed to equal just x. Now, you might wonder, well, what in the world is the point? Well, here's the point. If I were to look at an expression like this one, 5 raised to the log base 5 of x, and I was asked to simplify that, this would equal x. Because 5 raised to the log base 5, it's almost as if it cancels itself out. When I have the same base here and the logarithm, that sort of wipes itself out, leaves me with whatever that expression might be. In that case, x. If I have 10 raised to the log of 2.3, remember that log just by itself means that there's a base of 10 implied, so this expression is equal to just 2.3, wipes it out. The last one, I have the log base 2 of 8 to the x. So you notice, well, this isn't quite the same as it was in the example because here I have the same base in both spots. Maybe I can change 8 just a little bit. 8 can be rewritten as 2 cubed. 8 and 2 cubed are the same thing, right? So I take 2 cubed raised to the x power. Well, when I have a power raised to another power, I will multiply the exponents. So I can rewrite that expression as the log base 2 of 2 raised to the 3x power. That's me multiplying those two things together. And now, thanks to my inverse properties, the log base b of b to the x is equals x. Well, the log base 2 of 2 raised to the 3x is equal to 3x. So I can use those inverse properties to simplify expressions, and eventually it's going to help me solve exponential and logarithmic equations.